talking about in-silico simulations of polymer pyrolysis. And sometimes engineers ask me, Peter, can't you do this? Can't you do that? Can you do this? Now, let me better say, this is something that we can do. And we may expand on this in the next 5, 10, 15 years. You may remember there's something like Moore's law, and over the last 30 years, Moore's law still means that within 15 years, the capacity of the supercomputers is approximately increasing by 3 orders of magnitude with respect to speed and volume of calculations. That means you can be 1,000 times faster in 15 years, approximately. As lots of problems with scaling there as well, I can tell you we will not be able to do 1,000 times larger problems on the same level of accuracy in 15 years. That's out of question, but we will be able to do a lot more. And this basically gives you a little bit insight where we are at the state of the art and what we will be able to do in the future. Polymer-derived ceramics, by the way, that's currently interesting. My presentation is there, goes to some internet server, comes back here and is broadcasted over there because I'm connecting through Zooms that everybody else can do that. Good. Yes, polymer-derived ceramics. You heard already this concept, taking some polymers and having some interesting properties. My focus since my PhD is on silicon carbon nitrogen containing system. Then for, I do not know, 10, 15 years, I drifted off in the PDC things in primarily the oxide containing systems, and I took on the nitrogen containing systems since 5, 6 years again. As some of you may know that I'm doing other things like high pressure chemistry and even more things, but they're in nitrites. So we claim that we know a little bit how these systems, in particular in computations, emerge and evolve. See it? No, please don't get your own thoughts. Applications, you have heard many of these applications for thermal barrier coatings. Yes, high performance fibers is definitely the topic of this PIRE system. Membranes for gas separation, University of Vienna, just a great thing. Drug delivery, everybody claims that it's good for that. Oh yes, let's hope you can at least sell it for that purpose. Whether it's good for lithium anode materials, it's certainly better than standard graphite, and has its advantages there as well. Good. And maybe you find a new application for this and can sell it accordingly. Friends of mine make currently here bones. They have implanted them in mice. The cells grows on this, and this month only they will take out the, I think it's an artificial 3D printed lower leg from a mice, and they will check basically, because the mice were running fine the last 3 months with that, and they hope that it worked. All right. Since 30 years, I hear from the experimental synthetical folks, in particular, the notion we can design the better precursor with chemistry and can gear the properties of our material that way. Then you talk with engineers or thermodynamics people who do the exposure of these materials to 1700, 1800 degrees Celsius, and they will tell you all depends on the initial composition, not the architecture anymore, because in the end, everything will go into the thermodynamically stable phases and so forth. So that's the ultimate question. Does your precursor matter, and how will it matter? And yes, I'm working as a chemist, material scientist, bottom up. I'm working with atoms. You will see very soon a couple of bouncing balls here where they move along each other. So this is the realm where we are looking at. Does it matter how these atoms are bonded in the first place? Because yes, you hope you have a potentially single source precursor, you do the ceramization, you're getting an amorphous ceramic. I stop there typically, yeah, because crystallization is completely different than afterwards. And the better question is actually, which property, if there are any, is impacted in which way by the architecture of your system? I tell you, we are not that far. But that's actually where we go. And we're investigating, I told you here, the SiCN and SiCO ceramics, meaning we have here polysiloxane, and there we have a general architecture of a polysilane, and whether the R groups are further cross-linking to other units and so forth, I'll leave this to you. That's only standing in a generic way for siloxanes and siloxanes. More humble questions. Humble for what we can achieve. What kind of reactions do occur? And from the point of physical chemistry, that's typically what I'm teaching, what mechanisms, you know, these elementary steps, yes, which proton hops where, which bond is broken or activated by that process, and how does it form? And can I then, as a chemist, by the choice of side groups, prevent or help that mechanism to gain more importance? Are these mechanisms reversible, or is this just in one direction? Yeah? So likelihood and rates, can I inhibit that? And you're desperately then making with everything that you're doing, can I see certain molecules evolving, gases and mass loss? Can I relate this to each other? And of course, I'm showing you some fortuitous data where this looks good. Yeah? And structure fragments that are evolving, and can I see something in the composition? And all of this is done in the context here in polysiloxanes and polysiloxanes. I have to tell you, yes, we also have some polycarbosilanes, and we even went back to the polysilanes to study one of the call it archetypical reactions in this. This may come in next year in one way or the other. Here, I do this along a case study. I'm using this fantastic polymer, which you find in the literature, depending on the year of publication, or no, better, the year of purchase of the polymer of the group under various names. So we can still see it under here on HTP 1800. They bought it, I think, before 2005, and I may still have in the fridge. Some of you may know it under Sarah said these brand names, and sometimes PMZ20. This is in particular nowadays a name that is used in China. There's PMZ10, PMZ20, PMZ50, and so forth. Sometimes you see PVMZ. This here just emphasizes that you have a typical part of your backbone where there is a hydrogen on the silicon and the methyl group. Just a hydrogen and nitrogen, and every once in a while, so approximately 20% of all your groups have the vinyl group replacing the hydrogen. All right, and currently, not the end of last year, the beginning of this year, it was not available with Merck, and Merck does not provide it, but it should be available as the Duracell 1800. And I have to give here my kudos to Ralph, because he probably saved part of a PhD thesis of one of my students, because we needed new stuff, and he was so kind and provided that polymer to our experimental. This is also how you sometimes see this, and if you study with Ralph, then you learn that, siloxanes typically have the tendency to form ring polymers, and in this particular case, I tell you that the 1800 is going to refer to the typical molecular weight of one of those ring polymers, of course, with a kind of distribution depending on the manufacturing process. All right. And we take this PVMZ or P, whatever name you currently choose, using 1800, and now we have to make a model. And of course, we know that each simulation and each outcome in the end will be as good as the model or the work that you put into your model. So what are we doing? Now, you see two different things, 1 and 2. Let's take a look at them. Let's take a look at 1. In 1, I don't show any hydrogen, just because there's too many balls. Yes, if you see too much, you don't see anything anymore. Let's take a look into 1. So, yes, now much smoother over there, a little bit different here. These are individual one-dimensional polymers. There are 3 running in the X, the Y, and the Z direction. They are nicely stacked in what we call a 3-dimensional rod stacking so that they can interact with each other. But these are infinite linear polymers. And if you don't like it, well, this is under periodic boundary conditions. Typically, the length is 15 of each individual string, or 10, depends a little bit what we do with them. And then there are 60 silicons in the end, packed together with this composition. If you do an optimization in this DFT stuff and so forth, we're getting a density of 1.3. Yes, approximately 5 cubic nanometer. Is this large? Is this small? 5 cubic nanometers in a simulation is relatively large. And you see here this has 500 or whatever atoms. We will see data arising from this. What you see here is another model where I then took another Saturday afternoon or something like this, when I'm not all too busy with administrative work in the department, and I made this cyclo, or the cyclic polymer. There's 30 silicons are in there. The molecular mass is suspiciously close to 1800. And if we optimize that, we're getting a density of 1.0, or we fix it at this density of 1.0. Now, this shows you one of those cyclic polymers. This is again under periodic boundary conditions, so the very same polymer repeats itself everywhere. And we even build this sometimes artificially, sometimes non-artificially. We build this in some models by taking one of these vinyl groups and connecting it to an SiH. So we do sometimes cross-linking, and we put this into the model. And of course, we can study then cross-linking in a perfect way, only pyrosimulation, which means vinyl group with SiH bond, or we can do cross-linking via polyaddition, which means vinyl group with another vinyl group. It's all what we can do. We can target it, we can set it up, and we can investigate each individual model afterwards. And how do we investigate this? Let me see. Come on, also the other one can rotate. So that you get a little bit of appreciation that it's really 3-dimensional and so forth. Okay. And how do we do this? We, in this case, use ab initio molecular dynamics simulation. So quantum chemically, hopefully correct, rather accurate, or best on the market that is available. We have typically no issues with parameter. I can tell you we have issues, but we know how to avoid issues. Yeah? And it's great for chemistry. It's great for chemistry because, yes, indeed, the Schrödinger equation is, even if under some approximations and so forth, being solved, but we have nothing better than that as long as we want to stay in the periodic models. And if we dare to, we could still say, oh, we have seen certain mechanisms, we can probe them even with higher accurate quantum mechanical methods if we ever dare to. One of the problems is it's computationally relatively expensive. Please look at this, a short simulation, what we currently call something like standard run, production runs, yes, is 100 picoseconds. That's a short time, yeah, in 6 weeks. So we need approximately half a year to 1 year for a nanosecond. And a nanosecond is a long simulation. And we are limited to some 400,000 atoms. You saw basic volume. And now you can estimate already the size. You have seen it before. The sizes that we can cope with is on the 1 to 2 nanometer. Box sizes, do not expect me to say anything about porosity or too much about porosity. Don't expect that we can say too much about microstructure. This is on different levels. We talk about chemical reactions. This is on the atom scale. That's where we can provide information. And lots of technical details in supercomputers here listed. That's good. All right. Then we take such a model and we heat it up. Don't be scared. We are heating this up to 2,300 Kelvin, not to 4,000. No, we don't do that anymore. Not to 3,000 neither. 2,300. Why? Because then within 6 weeks, we can observe let's say 5 to 10 reactions, not more. There are days where there's nothing new going on. Yes, rare events. And we could start to think about, oh, can't we use some propagators and more? No, we don't. And we made one observation. Basically, it has to do the moment the first, call them defects, or the first radicals are emerging in the structure, many of the systems tend to, from now on, I see quite a lot of reactions going on. So the rates are increasing then afterwards, but it takes some time before the first one actually happens. And now let's rotate them. Yeah, so this here is one just after, there's at the start at 2300. Everything looks intact. Yeah, and honestly, there is everything intact. This is a polysilane. This stuff we can heat up to 2300, and only after some time something emerges. Polysiloxanes, you won't see anything happening at 2300, except that it's wobbling around. You have to go to 2500 there. Polycarbosilanes, you better stay at lower temperatures. So there is a certain trend in temperatures. And yes, we really first did this at 3000 to see that something happening. And then we gradually decrease the temperatures, typically guided. We want to see something reasonable within 6 weeks, because we think this is an effort that one can expect in preparation and then in analysis. Here, we see it after 100 picoseconds of the simulation. So after the 6 weeks, here's what you get. And if you look here, hey, there's an H2 bond sequence. And here, there's a Ch4 around. Yeah? But it's messy. It's messy, and what do we tend to do? Oh, one of the I did not want you all to see you again. What we tend to do is post-mortem analysis. So this is after 100 picoseconds. We look at this, and yes, 1, 2, 3, 4 Ch4 have emerged. There is one H2, and here's an ammonia. Do you expect this by a pyrolysis of a polysilane? Perfect. You expect this. Now, why don't you see anything of a silicon oligomer or so? Because I count no silicon oligomers here. Think about it. We have 30 silicons in our unit cell. If I'm starting to eliminate silicon oligomers that have 6 silicons and 6 nitrogens and so forth, I'm done. There's nothing left anymore. Yeah? So that's basically one thing. And now that looks a little bit complicated, but I drag you through the color. Remember, we started with a polysilane. S-I-N, S-I-N, S-I-N. This is the backbone. I have vinyls and I have methyls in my side group. What happens to those? And this is what this color code refers to. Green is still a nitrogen. Blue is still a silicon, and black is still a carbon is attached to a silicon. Now here's the red. What's that? The red is a nitrogen which meanwhile has 3 silicons as neighbors, has given away one of its hydrogen and has connected transamination, and all these chemical terms come along. Oh yes, I can identify quite a lot of them. Yes, this is one of the early reactions that will always happen, even frequently without any gas evolution. Yeah, that's cross-linking. That's when you put your polymer into the furnace, what you have anywhere between 250 and 400 degrees Celsius. Yes, this is a typical cross-linking reaction. Then you see here these big fat black ones. If you look very closely, then the black ones are always between 2 silicons. This is a big fat carbon. No, it's just a regular carbon, which meanwhile has 2 silicons as neighbors. So this has reacted and has inserted from a side group into the backbone. And the archetypical reaction for this is, of course, in polysilanes. In this Kumada reaction, in the Yajima process, Yes, I can make polycarboxylanes from a polysilane that is methylated as a side group for these methyl groups inserting into the backbone. This is what in the post-mortem analysis you see here as well. And of course, then it's interesting. Was this a Kumada rearrangement, or was this just a cross-linking from one part of a polymer to another part of a polymer? So did it really flip between two silicons, or was it cross-linking more polymer-wise? So let's see what here we rotate. Somehow I like this rotating stuff because this gives a little bit of three-dimensional appreciation of that. So we observe at least the outcomes of the fundamental reactions, and with these simulations we have access to mechanisms and the full trajectories. Yes, and yes, we have a certain time resolution of these trajectories, and see, this is one of the parameters you have to be careful of. This is the time step of your simulation, and gladly I can tell you the mechanisms that we're observing do not depend, at least within our testing, on the time steps that we use in the simulations. However, there seems to be a little bit suspicion from my side that the rates we observe for some of these reactions depend on the time steps. So it's a little fishy. Yeah. So the vision that we have is, oh, we want to acquire this detailed knowledge. I'll show you a couple of more reactions very soon, and identify inhibitors and or activators. And the typical example reactions, I have already pointed on this in this example here of this silane hydrosilylation, polyaddition of viral groups, and network formation, elimination, and some rearrangements potentially of the Kumada type. So now comes a little bit of work that an undergraduate student has done, because I typically say I do all the simulations myself. You do not see here work of any graduate student. However, sometimes there's incredibly interesting work. It's enticing because you see those bonds involved and you see hundreds and hundreds of atoms, and you have to decipher this. And you know, grown-up professors do not want to spend the time for that, yes, and they hope that there are some undergraduate students. And in this case, there was one. Anna took that on, and what you're now going to see is, first, snapshots of individual steps of this hydrosilylation reaction under the action of a catalyst, and then you will see a movie. So what have we done? We have taken action. So I am the catalyst, and I strip off one of the protons from the vinyl groups, and then basically we let this bounce around, and after some time, really after some time, it is like, well, I do not know, I don't want to make any inappropriate comments here, but they found each other, and this is basically just before they find each other. Here you see the proton between the silicon, and here's the carbon, and oh, the proton was taken by the carbon, but now the silicon is very unhappy as a threefold coordinated cellular rest, and boom, it reacts then with the carbon and grabs it and forms that bond. And here you see this knowledge or this kind of reaction in the typical way. You may have seen this in many publications, or you may have glanced over this hydrosilylation vinyl group and SiH group. Yes, and here we have it again, and this now should give us the video for that. And here you see our already activated vinyl group, and the first step of the mechanism is almost always it gets the proton of the silicon. The silicon is now threefold coordinated, very reactive, and bingo, it forms that. So the mechanism in this reaction is indeed, if we believe that the catalyst steals the proton from the vinyl group, then the vinyl group takes all effort to get back the proton. It will take one of the first protons that is easily available in the vicinity. This will be the one from an SiH group, and then the next species, which becomes incredibly reactive, is a three-coordinated silicon that really does not want to stay three-coordinated and grabs everything around it. If the time allows, it will still take that carbon. We have seen other outcomes. It can turn away. Yeah? It can turn away and can make other nonsense. Yes, but here basically you see this kind of process. The good thing is we have meanwhile more than one, I have to say. Yeah? Well, typically, I mean, we have seen it means 3 times, 5 times with a certain security that it's not a single event. Yeah, as I told you, 6 weeks to wait for and always do the same. Yeah, we can say we also observe this as a thermally activated process. So when we do not need to preempt this action of a catalyst and rob one of the protons here at the carbon, it also works just in the simulation. You have to wait much longer, but it works. That's good. Hydrosylation. Been there, done that. Here you see again this kind of reaction. It steals the proton, and then the silicon comes along, and after some time, grabs it. Come on, take it. Yes, good. Polyaddition. Nothing is easier than that if you activate this by a catalyst, because you see the proton on one side, you see the proton on the other side, and now you have 2 radicals. And in all these quantum simulations, it turns out that if 2 radicals will meet, you see this is significantly slower because when they meet, it's an incredibly fast reaction. You do not have to wait. The only problem in this reaction is that they come spatially close to each other. Yes, if they sniff each other in a distance of 3 to 4 angstroms, boom, they run to each other and will form a bond. There's nothing that that holds them, and then you have that. Now, if you now think about, hey, you're taking away the protons, how will the protons come back? In this simulation, they don't come. We later on say, this is now the stage of cross-linking. Now I can think to prepare the next model for further pyrolysis. Then I put back the protons. The protons don't come back by themselves. If I take them out, I have to bring them in. Good. This is not in this thermally activated process that I spoke about in the other place. The thermally activated process has all the protons in it from the beginning, and we don't need to do anything else. Yes, and then it only depends on how much time you spend. I just want to tell you here, you see here some 25 atoms. The model had anything between 300 and 500. So you need the skill to figure out what is happening where, and you have to start coding a little bit. And yes, I will take the first order, no, the second nearest neighbor, no, I may in some cases also use the third nearest neighbor for all the involved atoms, but it should still be less than 25 atoms, because trust me, when I start to display here more than 20 or 25 atoms, we cannot, with our eye, which is just a great analytical tool, decipher the mechanism with our eye. Yes, I can still put this on a potential energy surface and do in the computer, but I want to see it. And this takes a lot of time, actually. Yes, one has to go through this data more or less one by. Boring formation. It is usually a result of either the silicon lost its hydrogen. You see, one of the other outcomes, the alternative outcomes of your hydrosylation process, yeah? Or this hydrogen on the nitrogen became a little bit, well, it got some wanderlust, they say, yes, like Paul McCartney's song, yes, and it was just moving around, and all of a sudden, maybe then the next hydrogen moves in place here, and you want to form a 4-ring. And you see here beginning and end. Let me see if I click that. Yes, here we see the video that relates to this. And here was one attempt, and now the attempts are basically there. That's an intermediate situation, but for polysiloxanes, it happens way, way, way more often than for polysiloxanes. Yes? So the siloxanes really are not so avert against forming 4 rings, at least intermittently. And some of you who dwell on crystal structures of small silane oligomers know, hopefully, that there are way more crystal structures with SiN4 rings than ever have been discovered with SiO4 rings. Huh? So, good. And 6-ring formation. Yeah, again, you see this here. It was the start, was 4-ring. And this breaks up. I told you intermediate. And now we have a 6-ring. So you basically see all these nice things. Depolymerization reaction. Yeah. Everything is there under the sun. And, well, they lose each other basically. And currently, this is a very unhappy silicon because it has lost one of its bonds. It's essentially a radical. I write here, it's typically then stabilized, that its neighboring nitrogen is also two-fold coordinated. So formally, you can say, oh, maybe it's more double bond character, you know, from other quantum chemical studies that the strength of this double bond is not particularly high. So they are just waiting for something else to add to this and react it. And here we see another one. Here the outcome was SiH2, here the outcome was NH2, basically this guy over here grabbed one of the nitrogens and has all of them. Now this can sometime later, of course, go back again. All right, H2 formation. Let's see, basically, boom, boom, boom. Yeah, it will soon, this guy and some other here will form, and they are basically done. Yeah, it does not look exactly like the standard process that maybe an SiH and an NH came together. They formed an H2 and an SiN bond. It's a not so often process for the formation of hydrogen than this one, at least from what we see. Ch4 formation is already such a complicated process that we were so far not, or at least this is 9 months ago, not able to make a good video of that. This is the carbon that you see here. You see in the end there's a CH4. This is the other methyl group, which will give one of its hydrogens. Yes, basically, it's rotating up here. You see it then over here. This carbon has temporarily left as an CH3, maybe radical. I did not make a charge analysis of that piece. Yes, here's a very long bond of this to the silicon. Meanwhile, this here has gone over here, so it took a long way. Here's the proton shared between the two of them. Yes, and it took it, grabbed away, and moved on. Yes, it's basically it, how it came together. So there's tons of more trajectories, but essentially we can claim, we observe, we see it with our eyes, these individual processes, and basically what I was hitting on you in the standard process, you see interchain cross-linkings. You see basically SiN formation always goes ahead over SiC formation in all these polysilanes. And we have examples we claim where we have Kumada type rearrangements in siloxanes, and we have studied Kumada reactions in siloxanes. Now here's a little bit more I want to show you. And yes, I'm allowed to talk into the break I was instructed. So we stay with this polymer, and now we would like to connect this to a little bit more experimental size. Maybe some of you will feel more familiar with that. So we did some model. Actually, this is one of the first models that we constructed 3 years ago, because the simulations that you see here each took 1.5 years. On a typical 40-core supercomputer processor, basically 18 months approximately. So what we do for this is we ran all these simulations for 2 nanoseconds. I told you 6 weeks is typically hundreds, 60 weeks should be 1,000, and this is 2,000 picoseconds, approximately 2 years. And what we did was we took off all the gaseous species every 10 picoseconds that were evolving. We just looked at it. Oh, there's H2, away with it. There's some CH4, away with it. And as you can imagine, in the beginning of such a reaction, you see many of them. Then afterwards, towards the end, there's hardly anything escaping. And even better, in the beginning, you see, for example, here, lots of H2 emerging. And then H is already gone. It's high temperature. Or here, first you see carbon loss. After some time, you do not find any carbon loss anymore. And all the additional hydrogen loss is then more or less H2, because that's still available. So the loss rates depend a little bit on temperature. And again, that's our model. And I want to drive you to one last point, basically. What follows here is, oh yes, even in our model, if we do this under constant pressure, we see a densification. Please don't be scared that you see here 2,500 Kelvin, and it's not immediately exploding. Yes, the particular thing of our simulation that it will not within 1 nanosecond explode completely, but has time enough to even densify under these conditions. And yes, in the end, let me see what we get here. We see again the rotator. Oh, yes. Now we can look post-mortem analysis. How many carbon-carbon bonds have already graphite formation? We never get that far in these kind of simulations. As you see a couple of carbon-carbon bonds. And if we get lucky, very soon we will see a 5 ring and a 6 ring, but not too far in the simulations. Yes. More or less looks a little evenly distributed, but here's that 5 ring I was talking. And we go further, 2,000 picoseconds or 2 nanoseconds. We have lost 89% of all the hydrogens. But even in our final model, we have here 6 ring, we still have 1.6 weight% of hydrogen. So some people claim in this amorphous ceramics that they have less than half a weight% of hydrogen. You can do the analysis and see that half of weight% of hydrogen is still 5 atom% of hydrogen. Yes, that's, for me, 5 atom% of hydrogen is a lot in model building. Good. PGA curve. Oh, here this was the 2000. This is a PGA curve of this Sericel polymer. And of course, I show this to you because suspiciously or auspiciously, we're getting a mass loss of 21%. Experimentally, depends a little bit what kind of heating rate you used and how you prepared your initial polymer, but you will get anything between 20 and 24% experimentally in a cross-linked Sericel. Yes? So here we are at this level as well, but still 2.1% hydrogen in the material. Good. Go on. That's the last point with Sericel. Because we claim we do different simulations and we see very similar things. 1.2 nanoseconds, 3 pictures. The point I want to make is there comes another sequence of 3 pictures. Here we see all atoms, and I usually say there are so many you don't see anything. Here we only show the SIN bonded network. So take away all the carbons, take away all the hydrogens, show only the SIN. All right, looks like there's something missing. Then you look a little bit more closer to the CIH bonded network, and maybe with a lot of fantasy, you will see there's more carbon here or CH here than there is. So let's evolve the system a little bit longer. Let's go to 1.9, close to 2 nanoseconds. I think I had to take the data at that time at this level because I was going on a conference, and the last something like 6 weeks we're not making before the conference. So that's basically what this picture scheme. Everything, you don't see something. This is the SIN bonded network, and you may really say it is agglomerated here. This is the periodicity of that part, yes. And here is something open. And clearly in that pocket, there is an agglomeration or there is a higher density of carbon and hydrogen in that corner. So what we claim is in this simulation, simulations that are at 2300 Kelvin, 2100 degree, meanwhile can say, please, this is still 1800 degrees C, so quite high. However, you can do an experiment, shoot with a laser into it. You will have similar heating rates. You will have similar temperatures. So yes, it's not my fault that these experiments don't exist. I can do the simulations. You can do the experiments for this. We claim that even on a nanometer second, so take one of those femto lasers, shoot into it. You will see very fast, call it segregation, or what are other terms? This something of your material. It will segregate on the nanoscale. There's good reason for that. We have siloxane where we see its mechanisms frequently at high temperature. And so building up a condensed network is apparently for these systems not so easily possible to do this homogeneously in the way that your system stays homogeneous at the 1 nanometer length scale. It becomes inhomogeneous. Yes, and since we are going towards the end, the only thing I can tell you, yes, we have done this also here with this inorganic siloxane, this PHPS, done simulations there. Oh, rotating stuff, come on. I have one more thing here. PDMS, polydimethyl siloxane. That's basically model building here. And there we also done pyrolysis. We have done this simulated PGA, so that we see changes in composition. Please, this is an early slide. That is where you see here still from 3000. We can basically same thing also at 2500. However, then our simulation time is not 200 picoseconds, but 2000 picoseconds. Yes, but it still works. Yeah. So it's just a matter of time then in the end. We do this not single simulations. We've done this actually for a second one, and we claim we do not see significant differences. So we are hoping that once upon a time, either the Air Force or the National Science Foundation will pull over its horn of plenty over our head, that we have student funding, that they can do such work in more detail. And yes, that's more of that stuff, but there is a couple of things here where we go to this open networks, the carbon bonding. Do you see graphite? Not so fast, not at the 1 or 2 nanometer, not at the 1 or 2 nanosecond length scales, but we see already the development of some rings there. I want to have one last thing. This is the Sic Bonded Network. Come on. Yes. Want to catch up to experiments then as well, because in all our simulations, we see after some time in the siloxanes, this formation of these tetrahedra, or in other language, you would say, do you see this mixed tetrahedra where you have a silicon center and which is then surrounded by different numbers of carbons and oxygens? Because in your original polymer, the polydimethyl siloxane, you had exactly 2 carbons and 2 oxygens. Now, the answer to that question is yes, we see them all. So we see the development of this mixed tetrahedra. Nicely, you saw it basically rotating here. And this is one carbon that is meanwhile surrounded by 4 silicons. If you want, that's a nucleus of silicon carbide, at least in first order here. Coordination over there. All right, this should have been it. Yes. What do we learn? I mean, not only nice pictures, but we get a general feeling. There are fast processes and there are slow processes. Even on this nanosecond length scale, we can say there are fast processes. Yes, cross-linking, rearrangement, losses of some of these. Few carbon-carbon bond formation. This is what we call a fast initial process. And I claim, not my discovery, but this is definitely a discovery. the concentration and composition gradients that we observe in the simulations. I showed you here one example. I would be able to show you others. That's a fast process. It will be very difficult to avoid that, but if it's avoidable, we would be able to study this even with these quantum mechanically accurate methods. That's what I claim. Just give me money. Yeah. All right. And then there are slower processes. The slower processes are definitely the so-called segregations of larger carbon systems. Yes, I have a different set of simulations with a different approach where we will hopefully in the fall, after 1 year of writing, because I did not have enough time, publish that this concentration gradient precedes carbon-carbon formation. It's something like it has to make space, so where the organic groups then assemble and whoop, they will form then. They will do their business once they have given the space. Still, carbon-carbon segregation, here this is one of the things, needs almost all the hydrogens to have left the system, because otherwise the hydrogen will always stabilize whatever you call this polyaromatic carbons or partially aliphatic components. And it's only a question of wait and see, because if you just wait long enough, another year and another year, the simulation will progress. Open questions that we have in the future, I mean, I would claim we meanwhile have way more open questions, but Kumada type rearrangements, so the insertion of the methyl group into the backbone, I claim check, we have observed it, we just need to make the videos for that, and much more. This is the direction we want to take in the future. Well, we have a reactive force field for siloxanes. Shall we tomorrow explain you the those that are German among you know the Leiden des jungen Werther. Yes. So this is a painful endeavor of a PhD student who works on empirical potential simulations for something. Wait a second. I did my PhD 26 years ago. That reminds me of myself. Yes. But essentially, that's one way of to go. I mean, that's a buzzword. We know that for these things, it's not likely to work as easily because we're talking about elevated temperature simulations where machine learning potentials, you probably need a new machine learning potential for every temperature that you're. Yes, but that's a different story. Yeah? But we would like to extend the length scale and the time scale of our simulations. Of course, that's where we're all doing. So we can see chemistry. Hey, in action, in situ, in silico. In silico just means in the computer. That's it. Routine simulations, 100 picoseconds. Take this along, couple of 100 atoms, 100 picoseconds, that's the state of the art. And if you see 1 or 2 nanoseconds, yes, then somebody has too much time to spend on a supercomputer and had a generous funding agency. That's good. We see fast processes, we see slow processes, and I think it's a kind of surprise that certain things are fast that we may not have seen that way before. And they are, of course, very slow processes. Come on, crystallization is extremely slow. Yes. And we see the impact of the precursor architecture. I have not shown you some results of polydiphenyl siloxane. There's one big fat phenyl on that. You don't see any Kumada arrangement there. The carbons come from other things into the backbone, but you see them in the backbone appearing after some 200 or 500 meters. Good. That's it. I thank you for your attention, please. Hannah is going to start her PhD very soon. She got so completely excited that she decided to go to experimental studies.
That was one of the conditions, right?
I like to have this vibrant, exciting conversation all the time with folks who know way more about ceramics and polymers than I do. I like my funding agencies, and I thank you for your attention. And if you have any more, I was going to say problems. If you have any more questions, don't hesitate to ask.
Thank you, Peter.